So what I have planned for today is to get us started on chapter 10, which is on carboxylic acids and their derivatives. It's going to be essentially our last traditional organic chemistry chapter. After that, we have a chapter on amino acids and polypeptides. And we also have a chapter on polymers, which I still need to get class notes for you. That will probably get done over the Thanksgiving break. But there is not a huge rush for that because we still have chapter 17. But I do have it in the back of my mind to get that done over Thanksgiving break. So we have 3 days to cover chapter 10 because it's going to be on exam number 4, which again is going to be the day we get back from Thanksgiving break, that Monday. So not this coming Monday, but a week after that. Good. So if there's time after what we discussed today, I think I might just review something quickly from the carbohydrates chapter. It occurred to me that it probably wouldn't do anyone any harm, again, assuming there's time, if I went over 2 rather similar looking reactions of monosaccharides, which is the exhaustive alkylation and the formation of glycosides. So if we have time, I don't think it will do anyone any harm to go over that again. I want to make sure we're not confused about that. So when we talk about carboxylic acids, I'm assuming that you remember what carboxylic acids are. They're compounds of this type. R can be either H or alkyl. But there's also various compounds that we consider to be derivatives of carboxylic acids, or compounds that are related to carboxylic acids. And they include esters and amides, as well as acid chlorides. And really, we have to throw nitriles into the mix. Although they look a little different because they have that triple bond, really they belong in the same general class of compounds in terms of how they behave. So, of course, with esters, remember you have these 2 R groups. They can be either the same or different. We do require that the group R2 not be a hydrogen, because if R2 is hydrogen, you don't have an ester, you have a carboxylic acid. As for amides, the way I like to define them is by leaving these 2 bonds on nitrogen undetermined. They could be to either hydrogens or alkyl groups. Either way, you've got yourself an amide. Acid chloride, of course, I think is pretty self-explanatory. Oh, and I guess there's another one that really we mentioned in the carbohydrates chapter. I want to make sure that we get that one mentioned. This is called an anhydride or an acid anhydride. It's essentially what you would get if you took 2 carboxylic acid molecules and removed water to join them together. You would get this functional group known as an anhydride. There's no particular structural reason why the 2 R groups have to be the same. In other words, one could imagine a molecule where the R groups are not the same, but I think in practice you'll find the 2 R groups are always going to be the same. And acid chlorides and acid anhydrides are almost identical in reactivity. You can consider them to have the same reactivity. So those are carboxylic acids and their derivatives. I also want to talk a little bit generally about the types of reactions that we're going to cover in this chapter, though I think we'll really mainly get to reactions starting on Friday. But that is nucleophilic acyl substitution. In chapter 9 on aldehydes and ketones, we talked about nucleophilic acyl addition reactions. Those are the types of reactions that aldehydes and ketones undergo. But carboxylic acids and their derivatives react a little differently. They tend to undergo something called nucleophilic acyl substitution. And you already know the word substitution. It implies that there's going to be 2 groups that switch places. And that's certainly going to be the case with these types of reactions. But just speaking very generally, if we have some carboxylic acid or carboxylic acid derivative, where I'm just with some group Y over here, and you can see that can be OH or 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 the amide nitrogen and so on. But if you have some compound of this type and you treat it with some nucleophile, we would expect to get a substitution reaction. That would give us a product that looks like this. And then presumably we would lose that other group in some sense. But instead of the nucleophile just adding to the, like it did to the aldehyde or ketone, and we got things like, we've had things like hydride addition, reaction with lithium aluminum hydride or sodium borohydride. We had things like formation of hemiacetals and acetals. That was an example of a nucleophilic acyl addition reaction. Instead, we're going to have a substitution reaction where this nucleophile or Lewis base takes the place of this group Y. And that in general is what we're going to see in chapter 10, is reactions of this type. Though I think, again, largely we'll start to see that on Friday. But we're going to start out focusing on carboxylic acids. That's probably what we're mainly going to be talking about today. And carboxylic acids show up everywhere in nature. There's certainly carboxylic acid functional groups and lots of biologically related compounds. In fact, we saw some just the other day when we were able to convert simple monosaccharide to one of those aldaric or aldonic acids. And I can never remember which is which, but both of them had carboxylic acid functional groups. So those will show up in metabolic pathways. You've got one very famous carboxylic acid that your book mentions, though I don't think I care if you memorize the structure, is salicylic acid, which looks like this. Salicylic acid has its uses. Well, before I get to their uses, though, I have to say salicylic acid has been known as a component of willow tree bark for over 1,000 years. And it has some uses in its own right. It's used in medication for skin conditions like acne. It's used to treat warts. Salicylic acid used to be used as an analgesic, but it's kind of hard on the stomach because it's got these two acidic functional groups. Phenols are quite acidic, and the carboxylic acid functional group is, of course, even more acidic. So what a little company that you might have heard of called Bayer came up with is, I'll just do some eraser chemistry over here, is replacing the phenol group with an ester. They made an acetate ester. In fact, in this chapter, we're probably going to learn how that's done. But acetylsalicylic acid is also known as aspirin. And that's not quite as harsh on the stomach. So this is something that comes from a naturally occurring material that we get from a plant. And so now we make tons and tons of this stuff every day. But other acids you might have heard of include formic and acetic acid, which we'll introduce shortly when we get to nomenclature of these things, since I saw a problem in your book that I thought would be good to do in class. So we'll go over a little bit of naming, just so you see how naming carboxylic acids works. But be that as it may, I should also mention this type of nucleophilic acyl substitution reaction is very, very common in living systems. I don't think we're not going to do a chapter on metabolism, but if you look at metabolic pathways, you will see reactions of that type all over the place. So other than that, I think the main thing to get to besides naming of carboxylic acids is I also want to say, since as I said, at first we're going to focus on carboxylic acids. We'll get to esters and amides and so forth on Friday and Monday. But one thing that we should say about carboxylic acids is they are planar. Of course, that carboxylic acid carbonyl is carbonyl carbon is sp2 hybridized. So here I'm even trying to draw it in the correct trigonal planar geometry. So it's planar at that carbon. Carboxylic acids do have some tendency towards nucleophilic addition rather than substitution, like aldehydes and ketones do, but much less so. And the reason for that is because while carboxylic acids do have this other resonance form, which we talked about quite extensively in the context of aldehydes and ketones, this resonance form shows how the carbon has a partial positive charge and so is subject to attack by nucleophiles. Meanwhile, the oxygen is a partial minus charge, so it's subject to protonation. But in carboxylic acids, there's, and the same would be true of esters, by the way, there is another resonance form that shifts that partial plus charge off of carbon onto the oxygen atom. That's a lone pair. It didn't come out so well. And so as a result, there's less partial plus charge on that carbonyl carbon of a carboxylic acid than there is for an aldehyde or ketone because of this additional resonance contributor. So that means that carboxylic acids are less likely to undergo nucleophilic addition. They tend instead to undergo nucleophilic acyl substitution reactions, which again, we're going to largely get to on Wednesday and Friday, probably mostly, I'm sorry, Friday and Monday. Good, let's see. I think that's enough for the introduction. Any questions so far then? Let's see then. In terms of, oh, I'm sorry, oh, over here. Got it, you're like. Nucleophilic addition than aldehydes and ketones because of this extra resonance contributor. That's why they undergo nucleophilic acyl substitution instead. They're more likely to do that. And the same is true of esters and amides, and we'll get to all that eventually. So I guess another way of answering your question is to say, we're going to see that the reactions that carboxylic acids and their derivatives undergo are a little bit different from the reactions that aldehydes and ketones undergo. That's another way to put it. Good. Other questions then? Well, I want to kind of leave those headings up there. So if you'll indulge me in erasing my board this way. A few notes then on nomenclature of carboxylic acids. A point I've made before is that if you know how to name alkynes, you know probably 90% of what you need to know to name anything. And there are, of course, some differences. Carboxylic acids tend to have the ending oic acid or ic acid on their names. I would say two trivial or non-IUPAC type names that I think are worth knowing are the two smallest carboxylic acids, which you'll certainly have heard of at least one of them. The one carbon carboxylic acid, normally, I mean, you could call it methanoic acid, methane, methanoic acid, but no one ever calls it that. People call it formic acid. Using that same type of prefix as in formaldehyde, because no one calls that methanal either. They call it formaldehyde. So that's the smallest possible carboxylic acid. You find formic acid in things like bee and wasp and ant venom, so it's very irritating to the skin, nasty stuff. Acetic acid you will have heard of. Probably even used it once or twice in, I don't know, high school chemistry lab or something like that. So again, you could call it ethanoic acid coming from ethane, but no one ever really does. People call it acetic acid. And you'll find acetic acid in vinegar. Vinegar is a solution containing, among other things, maybe round about 4 or 5% acetic acid. After that, the names start getting regular. So the 3-carbon carboxylic acid, whoops, what have I done? Started to draw another acetic acid. So this one you would name after propane. You'd call it propanoic acid. Though it also is another name, but you can go on from there. Butanoic acid, pentanoic acid, those names are perfectly acceptable and everyone would recognize and understand them. Your book has some interesting naming problems. So if you don't mind my plagiarizing straight from your book, I took this from problem 10.2 in chapter 10. It says to name the compounds, and the first one they give you is this one. And I would simply call that one phenylacetic acid. Whoops. Because all we've done is replaced one of the hydrogens on acetic acid with a phenyl group, with a benzene ring. So I think phenylacetic acid is the best name for that one. The next one looks something like this. Another bromine over here. So that's the next one. And I would name that one as a propanoic acid derivative. So carbon 1 is going to be your carboxylic acid carbonyl, 2, 3. There's 3 carbons, so we'll name it as a propanoic acid. And we'll just observe that there's 2 bromines on carbon 3. So I think the best name would be 3,3-dibromo propanoic acid. The next one looks like this. And I think we would need to name that as a 4-carbon carboxylic acid with, again, carbon 1, of course, being the carboxylic acid carbonyl carbon by definition. So this would be named as a butanoic acid, but there's also a double bond starting at carbon 2, between carbons 2 and 3. And not only that, the double bond is trans. So I think the best name for this compound would be trans-2-butene oic acid. And you would remove the E after 2-butene. 2-buteneoic acid. I think that's the best name. Or if you wanted to, you could also call it E-2-buteneoic acid. Perfectly acceptable. Either way is fine. I have no preference one way or the other that way. And then the last one looks like this. So again, with carbon 1 being over here, we'd keep counting 2, 3, 4, 5. And of course, it doesn't matter which of those 3 methyl groups we call carbon 5. All of those 3 methyl groups are equivalent. So we would name this as a 5-carbon carboxylic acid. We'd name it as a pentanoic acid. And all we'd need to say is that on carbon 4, there are 2 methyl groups. So I think we'd want to call that 4,4-dimethyl pentanoic acid. I just thought going over that a little bit might be helpful. There might be some nomenclature questions on OWL. So it's good to review a little bit of that. It's also good review for the final exam, since the final exam is cumulative. Good. Let me see. Couple other things I should say about carboxylic acids in terms of their properties. First of all, they are quite polar, as you can imagine. So certainly the smaller carboxylic acids are going to be water soluble. I think up to about C4 is water soluble. After that, they start getting greasier and greasier, and eventually you wind up getting literally fatty acids if the carbon chain is long enough. So so after some point, they stop being quite so water soluble, but they are quite polar. So we would expect properties that we would associate with polar compounds like water. Certainly, they undergo hydrogen bonding like water. In fact, almost as a little aside, one intriguing property of carboxylic acids is they tend to dimerize by hydrogen bonding. And you get structures that look like this. I'm here showing the hydrogen bonds as a dotted line. So that means it's going to be harder to get carboxylic acids to boil than less polar compounds of a similar molecular weight, because you have to disrupt those hydrogen bonds. So carboxylic acids do tend to have that behavior. Other than that, I guess I should mention another property common to carboxylic acids: they tend to smell bad. You know what vinegar smells like, and that's a very dilute solution of acetic acid. I could give you a couple other examples of slightly larger carboxylic acids. Butanoic acid, which is 4 carbons, is also called butyric acid, from the root meaning butter, because butyric acid is found in rancid butter. And I don't know how many of us have had to deal with rancid butter. Generally, we refrigerate things and we're careful, but if you've ever come across it, you know rancid fat is not at all pleasant smelling. Another example of the same, hexanoic acid, which has 6 carbons, is also called caproic acid. That comes from the same root as in Capricorn the goat, because caproic acid smells like billy goats. So you get the idea. These things tend not to smell good. The only point at which the bad odors tend to go away is where the carboxylic acid gets pretty much into fatty acid status, where the chain becomes long enough that it's just no longer volatile. So generally, they have to be at least 15 or 16 carbons in those cases. So that, I think, is all we really need to say about that. Questions on sort of this page that I've drawn up here, or on naming or anything like that? So much, I think, for the sort of physical properties of carboxylic acids. Let's talk a little bit about the chemical properties of carboxylic acids, namely, as you might guess, their acidity. They are called carboxylic acids, after all. Thing was being stubborn. Okay, so carboxylic acids are acidic. Generally, their pKa's are around 4 or 5, somewhere in that area, which is, I don't know, a trillion times more acidic than water, let's say, something like that. And the reason for that is because, I think we've talked about this a little, but it bears repeating. It's because the conjugate base of a carboxylic acid is resonance stabilized. So for instance, if we consider acetic acid, which has a pKa of 4.76, I don't really care if you memorize that, I'm just putting it there for reference. If acetic acid acts like an acid and loses H+, you get its conjugate base. Whoops. Which of course looks like this. And that conjugate base is resonance stabilized. What am I doing? It has another resonance form that looks like this. Remember, of course, whenever we're talking about resonance, you're not allowed to move any atoms. You're only allowed to consider different ways of distributing the electrons. So what that means is this minus charge on oxygen is delocalized. It's partly on one oxygen and partly on the other. If you wanted to consider the true structure of the acetate ion as being some kind of hybrid thing with a -1/2 charge on both oxygens, I would be okay with that. That would certainly not be wrong. It's kind of hard to draw that, but that would certainly not be wrong. If we compare this, just as an example, to ethanol, is what, sorry? CF, compare. Yes. If we compare that to ethanol, which is a very fair comparison, both compounds of 2 carbons, ethanol will have a pKa around 18 or something like that. If ethanol loses H+, then you get the ethoxide ion. and that's the conjugate base of ethanol. And in terms of atoms to put a minus charge on, you could certainly do a lot worse than oxygen. Oxygen is quite electronegative. Certainly much better to put a minus charge on oxygen than on nitrogen or carbon, let's say. But here, the minus charge is localized on this oxygen atom. There's no way of stabilizing it. It's just all sitting on that one oxygen atom, as compared to an acetic acid. That negative charge is delocalized and shared amongst two oxygen atoms, or shared between two oxygen atoms. And so that's the reason for this really big difference in acidity. Remember, the lower the pKa value, the more acidic the compound. And also remember that the pKa scale is logarithmic. So this is something like 13 orders of magnitude. Acetic acid is something like 13 orders of magnitude more acidic than ethanol. Call it 10 trillion times more acidic, and you would be in the right ballpark. So it's a pretty dramatic difference that we see because of the electron delocalization in the acetate ion as compared to the ethoxide ion. And we've made this point before, which is in general, and I'll write this down, it's in your class notes, but I want to write it down also. But in general, anything that stabilizes a conjugate base, anything that helps to spread out the negative charge on a conjugate base makes the conjugate acid stronger. So anything that stabilizes a conjugate base makes the conjugate acid stronger, or makes its conjugate acid stronger. And generally, we see that stabilizing by way of spreading out the negative charge. So anything that does that for us at all, such as by resonance, is going to make the conjugate acid stronger. And that makes sense, because if you make the conjugate base happier by stabilizing it, then you make the conjugate acid more willing to give up H+. So again, this is stuff I think we basically had in chapter 1 or 2, but it bears repeating. It's an important concept in this chapter as well. So just to give another example of all this, I looked up some more pKa's for you, and I sure don't care if you memorize all of these. I'm just doing it as an example, just to illustrate this whole thing about stabilizing the conjugate base. So let's start with acetic acid, and we'll put pKa values here. We know this one is 4.76. And what we'll do is we'll replace one by one each of these hydrogens with a chlorine atom. Remember, chlorine is quite electronegative. So at first you'll get chloroacetic acid, and then you'll get dichloroacetic acid, and then you'll get trichloroacetic acid. And what we would expect to happen is, as we're attaching chlorines, these chlorines are sucking electron density away from this part of the molecule like mad. So if and when we lose the H+ and we now have O-, the chlorines are going to help to spread out the minus charge, spread out the electron density. They'll suck some of the electron density toward it. One chlorine will do so a little bit, two chlorines even more so, and three chlorines more so still. So we would expect the acids to get stronger and stronger. We'd expect those pKa values to go down. And indeed they do. This one happens to be 2.86, this one 1.35, and this one over here 0.66. By the way, a question I often get at this juncture is, can pKa values be negative? Oh yes. For one of your super strong acids like HCl, absolutely, you will get a negative pKa value. So, but that I think illustrates the point that anything that makes the conjugate base more stable. Anything that helps to spread out that negative charge over a larger area of the molecule, larger surface area, let's say, that's going to make the conjugate acid stronger. Good. I think that's all I really need to say on that. Besides this, we'll spend some time on some of the reactions that carboxylic acids undergo. Mostly we'll talk about that next time, but I want to say a little bit more about the acidity of carboxylic acids and show how they can be deprotonated. And then we'll say a few things about how carboxylic acids can be prepared, including at least one way that you know already. And then I think that will be good for the day. Questions? Trying to think if I have enough space here in order to, I'd rather make a little more space if you don't mind. I mean, why should I try to squeeze it in? I could use a bigger eraser. Anyway, okay. So what about conversion of carboxylic acids to salts? You could say treatment of carboxylic acids with a base. And you will get, again, to make a salt, to make a salt of a carboxylic acid. This is pretty easy to do. You can take pretty much any carboxylic acid you like. I'll just use R over here. And you could treat it with any old base you like, such as sodium hydroxide. And you will get the carboxylate salt, in this case, the sodium carboxylate, since we used sodium hydroxide, and you will also get water out of it. If you wanted to have a balanced equation, then you would also get water. But you don't need to go nearly as far as hydroxide. Hydroxide is a way, way stronger base than you need to deprotonate a carboxylic acid. You can even use something like baking soda, which is sodium bicarbonate. NaHCO3. The bicarbonate ion is a much weaker base than the hydroxide ion, but it's more than strong enough to pull off the proton in a carboxylic acid. I think carbonic acid is a pK of like 9 or something like that. I should know, but I don't, not off the top of my head. But you would again get the sodium carboxylate, and at first you would get H2CO3, but H2CO3 carbonic acid, that's unstable. That's what you find in your Coca-Cola, by the way. That's the bubbles. And so H2CO3 breaks up into carbon dioxide and water. So those are the two inorganic side products. But either way, you get the salt of the carboxylic acid. And we've talked about that already. We talked about how you can make soaps by deprotonating fatty acids, and we talked about other ways of making them from esters of those fatty acids, and always it involved a base. And so we talked about how you can make fatty acid salts like this. And these don't have to be fatty acids. They can be smaller carboxylic acids as well. Point being, you can use any reasonable base to deprotonate a carboxylic acid. You don't even need to go as far as hydroxide. Your book mentions hydroxide, and they're right. But I just wanted to make the point that you don't even need to go as far as hydroxide. Even bicarbonate is a more than strong enough base to pull off the proton on a carboxylic acid. So with that, I wanted to talk about a couple of ways of preparing carboxylic acids. And we'll start with one that you know already, which is oxidation of a primary alcohol or aldehyde. With Jones reagent or something similar. So we talked about that in chapter 9. And we talked about primary alcohols in the chapter in alcohols, which is chapter 7. So this is a reaction we've talked about already. It was in chapter 9. And we know that you can take any primary alcohol or any aldehyde and treat it with Jones reagent. There are other reagents that will do this as well, like potassium permanganate would do it. Remember, Jones reagent is essentially CrO3 or H2CrO4. They're the same thing. H2CrO4 is just the hydrate, it's chromic acid. And you would expect to get the carboxylic acid out of that. Indeed, if you treat the primary alcohol with Jones reagent, it will at first convert it to the aldehyde, but then it will keep going. It will oxidize the aldehyde all the way up to the carboxylic acid. And that's as oxidized as that carbon can get, by the way. There is not really a good way of oxidizing it any further. So just as an example, if you took, I don't know, benzyl alcohol, just because it came to mind, and you treated it with Jones reagent, I would expect that you would get phenylacetic acid. Or if you took 1 hexanol, 2, 3, 4, 5. Oh no, not 1 hexanol, hexanal. Well, there's a variety of oxidizing agents you could use. You could use Jones reagent, you could use potassium permanganate. Any of these really stupidly strong oxidizing agents will do. And not expect you'd get hexanoic acid out of that. So the R group can be pretty much anything you want. Which H, this one? Oh, potassium permanganate, KMNO4. You could also use Jones reagent. Any of those really strong oxidizing agents. This is a 4 over here. Good, and there's another way of making carboxylic acids from nitriles, which I'll get to next after we erase this board. But I just want to make sure there's no, just want to make sure I answer any questions. Questions on any of that, on the deprotonation, or everyone remembering this reaction from chapter 9, hopefully? Oh, there's a question? Oh, I hope it didn't just erase what you were going to ask about. I can do Control Z. Oh, okay. This CH2, it only oxidizes. Oh, wait a minute. You're quite right. Would not make phenylacetic acid. It would make benzoic acid. Good thing I didn't erase it yet. Good, thank you for pointing that out. So everyone, please make that change in your notes. It should just be benzoic acid. Because the way you could tell it was wrong is I added a carbon. That's no good. We call that violating the law of conservation of mass. We don't want to do that around here. So I'll leave that up there for a little bit. I'm very glad we caught that. I'm very glad you caught that because I sure didn't. Okay. Well, there's another way of making carboxylic acids from hydrolysis of nitriles, but I'm going to go in reverse order from your book. I'd like to show you first how to make nitriles, which nitriles are pretty easy to make. And your book again reference, or rather your class notes again reference chapter 6, which we didn't cover, but you don't need to have covered chapter 6. You don't need to know that it's called an SN2 reaction. But you can make a nitrile pretty easily by taking pretty much any alkyl halide, preferably primary. It works better if it's a primary alkyl halide, and treating it with sodium cyanide, which, by the way, let's just review what sodium cyanide looks like. And yes, that's the same sodium cyanide that's so terribly toxic that people are getting killed in old detective movies by someone slipping cyanide into their drink. Same one. And you will get a substitution reaction. And this time I do mean for that CH2 still to be there, because it should have the same number of, it should have one more carbon than what we started with. So you will also get, as a byproduct in this case, sodium bromide. And this doesn't have to be bromine either. That could be a chlorine or an iodine also. But this is just a nucleophilic substitution reaction. The cyanide and the halide switch places. So that's all there is to that. And by the way, congratulations, you just learned the main important thing of chapter 6 is that those you already knew about nucleophilic substitution reactions or substitution reactions in general. That's most of what chapter 6 was about. And I think it was perfectly safe just to skip it. I'm very happy we did. There's just a lot of complications in there that really I don't see the point of bothering with. Good, so that's how to make nitriles. So nitriles themselves doesn't have to have the CH2. I'll do some examples too. So nitriles can be hydrolyzed by heating them in the presence of dilute aqueous acid. And you can write HEAT for heat, or you can write a triangle. That's a shorthand for heat. And you will get the corresponding carboxylic acid. So the carbon that had been the nitrile carbon is now the carboxylic acid carbonyl. The nitrogen winds up in an ammonium ion, actually, NH4+. So that's an inorganic side product. So that's where the nitrogen of the nitrile ends up. So let me do some examples. Let's take benzyl bromide. We can treat that with sodium cyanide, and we will get the corresponding nitrile, or actually the chain extended nitrile, looking like this. Or we could just be given the nitrile. That's if we're not given it, we can also make it from the alkyl halide. But that nitrile then we could take and heat in dilute aqueous acid, and we will get the corresponding carboxylic acid. And this time it really is phenylacetic acid. This time I think I counted the carbons correctly. So that's an example of that type of reaction. Main thing to focus on is nitriles can be hydrolyzed to form carboxylic acids. And the fate of the nitrile nitrogen is in an inorganic side product. But these nitriles in turn can be made from alkyl halides. And again, that doesn't have to be bromine. It can be chlorine or iodine also. Not so much fluorine. The carbon-fluorine bond is really strong. And that, I think, leaves us in a pretty good place for today, though it doesn't leave me with enough time to review that other thing. We might have time on Friday or Monday, though, if it turns out to be a good thing to do. So I think we'll end things there. Have a great day. We'll see you all on Friday. Oh, I'm sorry, question. What are we doing where? Here? Yes, we're hydrolyzing it. Hydrolysis of a nitrile.